Welcome to this eLearn security video training lesson on debugging buffer overflows. In this video, we're going to debug the application called Good Password in order to inspect how our end can smash the stack, causing the application to crash. This will help us to understand what happens on the stack when a buffer overflow occurs. Let's start by opening Immunity Debugger and load the application. Before actually starting the application, we need to provide our input. We can do this by clicking on Debug and selecting Arguments. Here we will type the input. For now, let's just type some A characters and click OK to confirm. Immunity tells us that we have to restart the application in order for the changes to take place. Let's click OK and restart the application by clicking on the reset icon in the top menu. Notice that we can also restart the application with the shortcut key combination Control plus F2. Now we're good to go. While debugging the application, we'll also take a look at the source code. This will help us better understand all the instructions in it. The first step is to find the main entry point to the program. As we can see here, in the main function, the program prints the following string. The easiest way to find the entry point is to look for this string. Let's go back into Immunity and run the program. Once the program runs, let's search the string by right-clicking on the Disassemble panel and select Search for all referenced text strings. As we can see, we have all the strings defined in the program. By double-clicking on You are in Good Password, we will automatically jump on the disassembled section where the string is defined. In other words, we are now looking at the disassembled version of the main function. On the left, we can see that Immunity identifies the entire function with a vertical line. All the instructions in here are part of this function. Therefore, they start at this address and end here. We can double check that we're in the correct area of the program by disassembling the application with objdump. We already did it, and here's the output. This is the main function. On the left, we can see the memory address of the function. As we can see, the address is the same found in Immunity. Now that we know the main entry point, let us set a breakpoint at the beginning of the function. We can do this by hitting F2 on the keyboard. Let us now run the program with F9. It should automatically stop at the breakpoint just set. We're in the first instruction of the main. As we can see, EIP points exactly to the first instruction. As you already know, the first instructions when we enter a function are called prologue. This will create a new stack frame for the function. After the prologue, we can see that the program subtracts 20 to the top of the stack. This will make room on the stack for local variables. In the source code of the program, we can see that the first instruction sets the variable password to 0, and then it prints the following message on the command prompt. If we go back in the command prompt that Immunity automatically creates while debugging, we can see that right now there is no message in it. As we will see in a moment, once we hit the second instruction in the code, the message will appear. Notice that during the video, we will use the shortcuts F7 and F8 to step into and step over each instruction. So, let us step over a few times until we reach this instruction. This is exactly the first line of code in the main function, which sets the password variable to 0. The next few instructions instead we'll call the printf. The first one sets the string to print, while the second calls the actual function that prints the message in the command prompt. Let us step over right after the function call and check the command prompt. As we can see, the message is here. Let us go back to the source code and check the next instructions. First, we call the function buffer overflow, and then we check if the variable password is equal to 1. If so, it calls the function good password. Otherwise, it prints the message invalid password. If we go back into Immunity, we can see the machine code that does this. The first 4 instructions sets everything that's needed for the buffer overflow function. Then, on the 5th instruction, the program calls the buffer overflow function. This next instruction compares the variable password with the value 1. As you can see, this is the same address we used before when we set the variable to 0. Now, Depending on the result of the comparison, the program can jump to the instruction that calls the good password function, or it will jump to the instructions that print the message, invalid password. After that, the program continues by printing the last message, and then it terminates. So, this is how the main function works. Since we are interested in the buffer overflow call, let us set a breakpoint here and run the program. Now, let us step into it in order to inspect the buffer overflow function. Here we are. These are the instructions of the function. Let us take a quick look to its source code. The code is very simple. It defines the buffer, calls the string copy function, and returns. As usual, we have the prologue of the function and right after, the instructions that set space in the stack for local variables. Here's where the buffer will be stored. Before stepping into these functions, please note the current stack. As we can see, on the top of the stack we have the return address. This is where we will return once the buffer overflow function ends. To check where this address points, let us right-click on it and select Follow in Disassembler. As we can see, this is the next instruction right after the call to the function where we currently are. This is the value that will be restored in the EIP. So, let us go back and continue with our program. Right after the third instruction, we can see that the stack frame has been allocated. Once again, this is the memory area of the stack where the buffer will be copied by the string copy function. Let us now continue and see what happens. Here, the program calls the string copy procedure. Since the code of the procedure is defined outside the program, the code will automatically jump to its instructions. Notice that the string copy macro doesn't create a new stack frame. Instead, it will execute the instructions and simply return to the next instruction after the call. Let us step into a few instructions to see what happens. If we're right, we should start seeing our input on the stack. Indeed, as we can see here, the program starts copying it here. Once again, this is the stack address where the 10 bytes of the buffer variable were allocated. Once the program copies the whole input, it returns the instruction right after the string copy. Here we are. As we can see, the program works fine. Moreover, since our input is small enough, it didn't overwrite any other data on the stack. Therefore, the program will continue and terminate with no error. Notice that last byte of our input was copied here, while the return address of the function is a few positions ahead. As we'll see in a moment, if the input is longer, the string copy function will keep copying the input to the next memory addresses, overwriting all the important data of the other stack frames. So let us continue with the execution of the program. Here we can see the return instruction. Once again, since the return address in the stack is correct, we are able to return and continue with the execution. Now the program will compare the password variable with the value one. Since password is set to 0, it will jump to the invalid password message, and then it will print the last string before terminating. If we go in the command prompt, we can see all the messages. So, now that we know how the program works, let us see what happens if we provide a bigger input. So let's open the debug menu, select arguments, and copy the following input. We already know that with this input, we will overwrite the return address with the bytes A, B, C, and D. Let's restart the program, set a breakpoint to the string copy function, and run it. So far, the program did the same operations it did before. Here indeed, we can see the return address to the next instruction right after the buffer overflow function call, while this is the stack area where the buffer will be copied. Let us step into the string copy function and see what happens. As seen before, it starts copying our input in the stack. Let's keep going until it copies the whole input. As we can see, since this time the input is bigger, we're getting closer to the memory address where the return address is stored. And here we are. We have just overwritten part of the address with our input. Indeed, we can see that the string AB is in the memory address. If we continue, we can see that it will copy the other remaining characters too. Let's see what happens now if we continue with the execution. First, the program will return the string copy function, and will execute the instruction right after that. Right now we're in the buffer overflow function, and the next instruction was supposed to return into the main. But as we can see in the stack, the return address is not there anymore since we overwrote it. Let us step into it until we reach the return instruction. Once we run this instruction, the value on top of the stack will be copied into the EIP. Once again, this was supposed to be the address of the next instruction after the function call. Let us execute the instruction and see what happens. As we can see, the EIP now contains the value that was on top of the stack, but since it's not a correct address, the program crashes. Indeed, we get the following message. This is what a buffer overflow looks like. Now, an attacker that wants to exploit this vulnerability will craft a payload that replaces the EIP in order to get control of the program flow. This concludes our training lesson on debugging buffer overflow. We suggest you do the same with a helper program too, in order to see how the flow changes and how we can enter into the good password function. Thanks for joining us.